Good afternoon. It is a pleasure for me to introduce our next speaker today, who is Martin Zika, and he will tell us something interesting about NQP, manifolds, Courant algebroids, and Lagrangian relations. Thanks
Thanks a lot for the introduction and thank you for having me. Especially since it's my first research level talk, so I'll be talking mostly about the contents of my master's thesis. So this is the topic, NQP manifolds, so non-negatively graded manifolds with some extra structure, and how they relate to Courant algebroids, and how we can talk about those in the language of Lagrangian relations. So the plan is first NQP, second Courant algebroids. So this will be the first half where I'll basically review the construction of Rothenberg, who showed that they are in those structures, and those structures are in a one-to-one correspondence, or the isomorphism classes are in a one-to-one correspondence. Then we'll get to talk about substructures. Of those value structures, and we'll use it to define relations. And if there's some time left, which I'm a bit skeptical about, I will say a bit about quantization, functorial quantization of odd symplectic manifolds, and how it fits to this Lagrangian, this picture of Lagrangian relations. Okay, so let me define an NQP manifold. So definition: a NQP manifold is informally a manifold with graded coordinates. So they are non-negative and stands for non-negative degrees from 0 to infinity, and it's also equal with some extra structure, Q structure, a differential, and P. P stands for Poisson or symplectic structure. Okay, more precisely, is a certain local ring space, or more precisely, a graded local ring space. We call it M. It's defined over an ordinary manifold M0. So here M is the NQP manifold, M0 is the category of smooth manifolds. Okay, width. Following structure. So first, we need to say what N manifold looks like without the extra structure, and that's defined through the functions on this manifold. And the functions are just polynomial in those graded coordinates. Then more precisely, we can formulate it in terms of structure sheaf. So structure sheaf of this local ring space. So the local ring space is space. Let's say this space manifold with a sheaf of sections, which you can think of as functions on the manifold, and local global functions look like this. The product of the non-graded functions on the base manifold and a symmetric power of a graded vector space. So this is n-graded, so non-negatively graded vector space. And yeah, we can think of it as being spanned by write it down, span certain bases. Where those elements are said to have a degree, at least one. So in a sense, the coordinates on the base manifold are the variables of degree 0, and those generators of this vector space are the variables of degree something else. And the motivation here comes from gauge theory and BV-VRST theory, where I do not have time to recall it. Just very briefly, there we extend our space of fields to deal with, to effectively reduce our the space of fields to the one which is adapted to the constraints given by the gauge symmetry by introducing new fields. So by introducing ghosts, this can be ghosts, ghosts by analogy. And one doesn't stop there, then you choose other fields, you choose some kind of conjugate fields to the original ones and to the ghost as well. So anytime so those new coordinates can be thought of as corresponding to those new extended new fields and extended space of fields, where the coordinates on the base manifold can be thought of as the original fields. More specifically, for say Young's theory, it could be just gauge fields. So say one forms with values in the algebra. Okay, so this is the vector space, and S denotes the symmetric powers, which is just the well, it's a tensor power. It's consists of tensor powers of those variables, such that they are symmetric up to a sign. This is a graded symmetric algebra and a graded vector space. So you commute when they're odd, so when they're even, the degree is even. They're entire commute when the degree is odd. So we can think of those as a bunch of bosonic and fermionic coordinates, where the coordinates on M0 are just bosonic. Okay, so this thing here, let's say graded commutative associative algebra. So something like this, all come in a associative R algebra, but its N means that it's non-negatively graded and graded symmetric. Okay, so this is what the space of local functions look like, and of course, the manifold, so some kind of an atlas. I will not like describe it in detail, but it's just here it has to preserve this kind of structure, so it has to be more in this category. And yeah, a general function looks like a polynomial in those variables times some function or base manifold. Okay, so this is what an N manifold looks like. Now let's add the Q and P structures. Okay, so this is the first thing we specified, then the Q structure. So let's say the homological field. Called Q, and it will have degree 1 in the sense that it's a tangent field, so it acts on functions, and it like this. So there is one defining condition. The second one is it's homological, so it defines this condition holds, and it defines a coaching. And since this is I described the notion of homology theories. Okay, so that's the second structure, the Q structure, and the last part is the P structure, the Poisson. It says P Poisson, but actually talk about symplectic structures or non-degenerate Poisson structures. So the last piece is a invariant homogeneous symplectic structure. We have omega, and yeah, we can think of this in terms of awesome formal inverse of this. Let's see. Precise way to define the Poisson buckets, I suppose. Okay, so as a definition, that's the structure we have, and so yeah, so those coordinates do correspond to those and n-type fields and those new fields in the extended behaviorist gauge theories. This Q operator corresponds to the extended gauge transformation, okay, infinitesimal gauge transformation defined on this new space of fields together with ghosts and so on. And yeah, this symplectic structure is again something naturally defined in this extended space, and just as the old regular symplectic structure on a in symplectic mechanics, there the symplectic structure describes the dynamics, the Newtonian dynamics. Here it describes the dynamics of say the dynamics of the gauge, so how the gauge changes, and so it's just this kind of analogy. Okay. Okay, so now a few more definitions. So we need to know what a degree is, a degree of a manifold. So it's visible here. Is this visible?
Yeah.
Okay. So a degree of a manifold is defined as the highest degree of a coordinate. Yeah, so again, in this sense, by coordinates, I mean the actual coordinates of the base manifold and the ghosts and entities that generate those functions. Okay, now, yeah, I'm going to draw this picture. So, given an NQP manifold or just an N manifold, we have this kind of sequence. So here we have the base manifold. Here's the whole greater manifold, and from here we can forget about all the functions or the sections of the structure sheet with the highest degree. So here we can okay, so by definition, let's define it now. That n means the same greater manifold with coordinates up to degree n. So
you don't actually forget functions of highest degree, but some ideal generated by coordinates of the highest degree, and you portion it out or something.
yeah, it makes sense like through so it's like in this direction, and what it means is actually that we have in the other direction inclusion sheaves. So this is how I understand this. Just as I mean, I would define morphisms of great manifolds as morphisms of the underlying structure sheaves. So yeah, so those are the obvious inclusions of the yeah of the functions generated by those coordinates included here, and this is what I mean this map. So this is a precise thing. Okay, so we have this kind of a tower, or this filtration, and okay, so just to yeah, one thing that's interesting is this M1 part can be thought of, can always be thought of as a vector bundle. So this part can be modeled by a vector bundle. And the other maps here are kind of similar, but they're not vector bundle maps anymore because the structure group is not a linear group. It gets defined because you're mixing coordinates of different degrees so that they add up correctly. Okay, so there's the picture. Is the underlying structure or internal structure of every N manifold. Okay, now a nice property. Am I too low here?
Probably. Yeah.
Yeah. So like, is this line visible?
Still visible.
Okay, but yeah. Good. So there's this lemma. That on an NQP manifold with a homogeneous symplectic structure, the degree of the great manifold cannot exceed the degree of the symplectic structure. So, it's I will not prove it, but it's very simple because in algebra chart, which exists, we can use the whole proofs degree-wise thing. We can just symplectic form is a sum of terms in the form of dx wedge dp, and if there was a coordinate of a degree higher, then okay, one thing I didn't say, the degree is additive upon multiplication.
Sorry, you don't have to use the Darby charts. It's just because the tangent and cotangent bundles have to be isomorphic.
Yeah.
But because they are z-graded,
Yeah.
The cotangent bundle has the rank kind of labeled the other way around.
Yeah.
And if you just look at these, and because they are isomorphic as a graded vector bundles, graded vector spaces, they have to have the same rank. And if you look on the conditions, you end up with this space.
Yeah, sure.
So you don't have to use any special chart, it's just linear algebra.
Yeah, sure. I mean, in the chart, it's like easy to see, but it's probably easy to see in many other ways.
Maybe I have a clarification question. The lemma concerns the equality on the very right hand side, right? Did you write it correctly? What's the message in this?
Sure. The lemma is it's like it's weird. This is like
the lemma concerns the inequality between these two degrees, right? Sure. Okay.
Yeah. I mean, usually here you get equality because if you have like dx, dp, and x is of degree 0. If you have any coordinates of degree 0, then you need a coordinate of degree of the highest degree. So usually it's the same, but I mean we could have a graded manifold over a point with no non-graded coordinates. So then you could have something.
So there is an even stronger condition on the graded dimension of a graded manifold. Like if you have a symplectic form of some degree, let's say k, the graded dimension of the graded manifold has to be very specific regarding with respect to this k somehow. Yeah. Symmetrical along k half or something.
Yeah.
So, and this is just a consequence.
Yeah.
Negative degree.
Yeah. Okay. Yeah. Great. So that's.
Just a remark.
Yeah. Great. Thanks. So that's the lemma, and okay, here when I say a manifold of degree something, I will basically mean like this. So I will not talk about the manifolds without degree 0 coordinates. For an N manifold, this is the definition, but for an empty manifold, this is the definition of degree 0. Okay. So let's continue here. A lemma regards a missing structure from the BBRC theories. Q is always autonomous. So that means that Q always admits there always exists a function, a section of the structure sheet, such that this Q can be written like this. So this is that's precisely what appears in the BRST theories. And yes, we can think of this function as the action in BRST theories, or at least as a part of the action. We will see a more we'll see it in coordinates in a moment. Okay, and another property. is that this condition, so the logical condition, is a condition for S. And that's this. This thing, which again in physics is called the classical master equation, and it describes the, well, say, the Lagrangian variance of S. So it's a Q acting on S, Lagrangian variance of S. So I guess that's how we recovered, just in analogy, all the data from with regards to theories, and if you wanted to be more precise, we would use the AKZ construction, where we, but if we want to talk about actual fields, we consider them as maps between two graded manifolds, and we obtain the structure of graded brackets and the action as well, Hamiltonian function of Q, by lifting those structures from the graded target and source manifolds. So that would be the construction. Now I'll just talk about basically about the geometry of the target manifold. Okay, so last thing we need to say just about NQP manifolds is this theorem. It's the so-called Bachelor theorem. So yeah, there it's always some so now first let me say what splitting means here. It means that there is always a collection of vector bundles, such as we can form this thing. Vector bundle given as a direct sum, and yeah, yes. Where am I? Which can be written as a sum of vector bundles, where each of them is shifted by some degree. This degree shift means that we understand functions on this as having degree I. So here the definition varies. Sometimes you will see minus I here. So it depends on whether you shift the degree of in fibers it's vector spaces. So whether you shift the degree of the elements of the vector space or the dual, which is the functions on this bundle. And because in a moment we will be talking about dual, but functions on it's more maybe a bit more natural to just to define the shift as shifting the functions on this. Yeah, so there always exists this kind of a graded vector bundle such that the structure sheet on our NQP manifold or on an N manifold can be given sections of sections of this thing. We take the dual, so functions on E, and then we take the Grassmann algebra, and and with all the different sums here, different degrees, we can recover the graded symmetric algebra we have.
Maybe I would have one remark to this. This is somehow generalized version of bachelor theorem, because original statement concerns about supermanifolds.
Yeah, exactly. So yeah, it's like a famous theorem in supergeometry, and this is the version for n-manifolds. And I should know, if you have a reference, I think it was, okay, I think it's 2013 maybe, but I'm not sure. So this is the important thing that we can always think of. Write manifolds and n-manifolds in this way, but this word sum is also important. It means that it's non-canonical. So yes, so whenever we use splitting, we can only say something about isomorphism practice of guided manifolds, n-manifolds, and those vector bundles. Also, it's not true that we can say that it's the same thing like up to isomorphism, because the dimorphisms wouldn't. Yeah, there would be problems with taking just the naive morphisms from here wouldn't be. So this is really just a statement on objects. Okay, so that's the first part. And now let's say a bit more about Courant algebroids. Where's the yeah. So Courant algebroids are just vector bundles equipped with some structure, and the structure is say a straightforward generalization of a quadratic Lie algebra. So it's an oilification of a quadratic Lie algebra. So we have something like a vector Lie bracket and a pairing. And a bunch of axioms that will make it work as an oid. So definition. Courant algebroids. Case. And I will just sketch which data we'll be using. So we have the vector bundle over a base manifold. And we have a pairing hypervise, and it can have like arbitrary signature. Then we have a bracket on the sections. Which will be almost a Lie bracket. And the first part of the data is anchor. Which is a bundle map from TM, which enables in a way take derivatives of functions on M in the directions of the sections of E in some sense. Okay, now some axioms. I will not write them out explicitly or just write plus compatibility axioms. Combine those structures in natural ways. Plus, I think of this as a part of those axioms, but yeah, I just want to say that the bracket is this thing is lead up to say up to something. So this up to something can be understood in terms of homotopy algebras, but I will not use this language today. I'll just say that if we forget about the pairing or take a zero map instead of the pairing in all of the axioms. So, then the bracket is actually a lead button. So this thing kind of measures how much the bracket is not a lead bracket. So yeah, this kind of in this kind of situation we would have a Lie algebra. So the Courant algebroid is kind of a deformed Lie algebroid, and a Lie algebroid is it's we can think of it as a vector bundle on whose sections we have a Lie bracket, and by the Frobenius theorem, or a generalization of the Frobenius theorem, for a Lie algebroid we can always integrate into a generalized foliation. So those Lie algebroids are say, I don't know, algebraic models of foliations of underlying base manifold, and a Courant algebroid will have a deformation of this. Yeah, and first main theorem. Reutenberg from 2002. Is that Courant algebroids are in a one-to-one correspondence with NQP manifolds in degree 2. So here this one-to-one correspondence is we can just on the isomorphism. So let me just sketch the construction. What corresponds to what? So I'll be very brief, but even so, it's good to see what this Hamilton function S corresponds to the action in physics looks like locally important. So yeah, or a general Hamiltonian S. We can write it out in a. It always mostly looks like this. Given we are in an NQP manifold degree 2. So degree 2, the symplectic structure has degree 2, and by simple degree counting, we conclude that this must have degree 3. The function on the manifold section of the structure sheet. So we have to, find such orthogonal terms with whose degrees add up to 3. And there are just 2 of them. So, the first one. The other one. So here, first those size are here Courant to degree 1. So we will have 1, 2, 3. So that's this term of degree 3, and this is just a function of degree 0. And here we have degree 1, and P is the coordinate conjugate to the non-graded or X. But yeah, so that X and P add up to 2, the number 2 in the symplectic form has to have degree 2. So it's 1 plus 2 is 3. And again, this is a say structure constant of degree 0. And now maybe it's a good thing to say a bit about physics again, because this kind of a combination appears in the BVBRST formalism. This is basically precisely the BRST charge. So so it's the part of the action that we add when we introduce the new fields, when we introduce the ghosts, the extended stuff. In the whole action, that will also be the part of the action that was there before we introduced the ghosts, so just the dynamics of the gauge fields. This is the new part, and there will also be some gauge fixing fields, gauge fixing fermion. But yeah, this is precisely the structure constants satisfy the conditions of a BVBRST theory, and we can, if we think of the given great manifold as if we think of the of the graded vector space V as say the Lie algebra of a Young's theory, or more precisely the sum of Lie algebra and its dual, then we can then this defines precisely the RST charge or the gauge theory with this the algebra. Okay, so this is how we reconstruct the VRS theory on an NQP manifold in degree 2. The degrees are different than in physics. In physics, this is degree 0, but it's not a problem that there's a theorem that says that the homology, which is the important part, stays the same. It's just related. Yeah. So how do we use this to define the Courant algebroid structure? Well, for blah blah blah. Define the bracket and the anchor. So the bracket, one bracket, such that you have those structure functions. And yeah, the other part is the anchor. Similarly, you find the anchor to basically in coordinates look like this. So I'm using the same letter, so maybe I could use like tilde here. So then the anchor acting as a section of the Courant algebroid. And that's something in the tangent bundle of the base, so that acts on the function of the base. And this we require to be precisely given by those structure constants. And then we need to prove that basically master equation on the graded manifold and we want to CA axioms from the graded axioms.
Secretly, do not talk about the symplectic structure, or
Yeah,
you should maybe say.
Sure.
Tell you.
Sure. Okay, so this is maybe actually
because this
yeah.
caused the problem in the position of the index.
Yeah, sure. Yeah, it should be said before this stuff, right? Yeah. So this is how you get the bracket and the anchor from the graded manifold stuff, but the pairing is actually the much more simple because this construction is done in a splitting. So we find some collection of these bundles. We get this big graded bundle right there, and on the part of degree 1, we define the Courant algebraic structure. So the Courant algebraic structure is like the it's the degree 1 part of the splitting, and there, so maybe I should use another bracket. Yeah. So So the idea is that we define the pairing and the symplectic form to be precisely the same thing, where the obvious difference, the symplectic form is anti-symmetric and the pairing is symmetric, is dealt with precisely by the degree shift. So, so we continue here with the construction, and so the best way to write this is so we have this kind of expression, and okay, we were just oh my God, it's so here on the left side we have sections of the Courant algebroid and a pairing. So it's a bunch of results from new and new. And on the right hand side, we want this to be the same as this thing, as taking the Boston bracket of those thetas, and we can think of them as being corresponding to those e's by the construction in the splitting. So we have section that we can take, we can lift the index here in the middle, and that should precisely, the Grassmann algebra on that should precisely correspond to the function here. And but of course the difference here is that sections of the gray manifold, there's no grading here, so there's no anti-commutation. Here, those two things are odd because they so the picture is M0. Then we have the M1 part corresponds to the Courant algebroid E shifted like this, and then we will have another part, E2 part. So we're in degree 2, so we should degree 0, degree 1, and degree 2 stuff. So the degree 1 stuff is the corresponds to the Courant algebroid shifted by 1, and this shift precisely means that it adds the sign here. So this whole thing is now symmetric because this thing is anti-symmetric, the bracket, and swapping those two is anti-symmetric as well. Okay, and the last thing is to define the degree 2 thing. And okay, I just quickly go through the construction. Okay, so first we take this thing. So we kind of think of this as bundle of, say, ghosts and anti-ghosts, such that they have all degree 1. And here we have kind of x and theta coordinates. X are the coordinates on the base manifold, psi sections of this, and theta sections of that, say, this is very formally. And we want to add the degree 2 thing in such a way that we have a nice symplectic structure here. So those two are already conjugate. We need a conjugate variable for x. It's very simple to find. This. Take the cotangent bundle of E, and we shift the degrees in the fibers so that the degrees add up correctly. So here we have x, y, theta, and p. So one thing we added is the cotangent coordinates to the base matrix. And we want to do the same thing for this one thing. So if our so we want to somehow mimic this construction. So what we do, we embed this here, but we do it isometrically. So isometric embedding means that it preserves the pairing here and here. Here we do have the Courant algebroid pairing. If you forget about this, if we do not forget about this, then it's the Poisson structure. And here we have the natural pairing on pairs from something, and it's still we just take the dualities and then add it. Now this one, let's say E and send this to E plus, depending on the definition of the pairing here, then might be half. So this is an isometric embedding, and now we just pull back this symplectic realization of this along the isometric embedding. So this will be our basically M2 thing, and using this isometric embedding, it's easy to prove that this thing is actually get a symplectic manifold here. Okay, so this is the construction. Yeah. Okay, so finally, let's get to the relations and substructures. Okay, so so I don't have much time, so I will rush it a little bit. So theorem, this is part 3. Theorem. Other important theorem, this is the first one. And so I'll write it quite out and then I'll explain it. So do that. Choose. There are structures, whatever it is, on a Courant algebroid E, in bijection with lambda structures. M, where first E and M are, this is a NQP manifold V2, and this is the chronology that corresponds to it. And Courant structures are natural substructures of Courant algebroids. So I don't have time to define, to say that those are some bundles which are, isotropic with respect to pairing, involutive with respect to the brackets, and somehow compatible with the anchor. So natural substructures. And similarly for NQP manifolds. So there are submanifolds which are compatible with symplectic structures, so they're Lagrangian. The symplectic structure vanishes on those submanifolds, and also the action of the Lagrangian function S vanishes there. Okay, so these are just natural substructures, and this was seen by Scherer in the paper, in the homotopy symplectic paper with the fun title. And yeah, I'll just mention the group idea. The idea is if we have a submanifold here, to get the right subbundle here, we just forget about the degree 2 stuff. That's basically it. The other direction is more complicated. We have to add some stuff. So we find L, the subbundle of the graded manifold this way. For a given Euro structure L. So this means structure. And this n star means that we get a conormal subbundle. So the normal subbundle is just the subbundle of the tangent bundle, which is precisely the directions which are not tangent to this thing, and the star means that we take the dual. So basically we're gonna take the conormal moment, and since this is Dirac structure, so it's isotropic with respect to the bearing. This basically means that we are adding as much of the momenta p, because here we don't have the p momenta. That's what we added here and going up and finding the symplectic realization. So we're doing something similar here. We're adding momenta such that it works, and we basically just add them as many as we can, such that it still stays Lagrangian. That's the idea. Okay, second part is just to prove that our lambda structure, if and only if L is right. This was seen. Okay, I don't know the year. Very slow. I think it was 2010. Precise group for this. But I would say that this is actually very easy very nice to see again locally in coordinates. So locally in coordinates, you can see how each of the terms corresponds to each of those conditions of the structure. So compatibility with the bracket and compatibility with the anchor correspond with different parts of this S function vanishing on the submanifold L. Again, the third part check. Survivability. This side. This is very That's the proof idea. And now I'm running out of time.
Yeah.
So okay, so it's like a 3 minute or 5 minute extension. Okay.
I think it would be fine.
Okay. So I'll just draw the big picture. There's now. So now the idea is to talk about morphisms of those structures in a flexible way. The naive way is to consider bundle maps which preserve the structure, and or maps of grid manifolds and maps of underlying sheets which preserve all the structure, including the symplectic structure. But of course, that's not a general, so we will need to consider just symplectomorphisms, just diffeomorphisms. But there are a lot of interesting relationships of symplectic manifolds, which are not symplectomorphisms. And that's where the idea of the symplectic category comes in. Or, yeah, the idea is from Weinstein. There's a nice thing present and sums it up. Okay, so the idea is to consider, say, M2 and M1, the manifolds, and we want to define some kind of a relation between them, like this. We take the product. Those projections, and we take a subset of the product, specifically a closed submanifold, which somehow preserves the structure, and that's precisely in the sense that it's the the natural substructure. So it's a NQP manifold, and requires R to be a lambda structure. Okay, so instead of maps which preserve structure, I have a submanifold of the product which is compatible with the structure. And for some technical reasons, I have to consider M2 bar, well, which means that the symplectic form here is with a minus sign. It's not important. So okay, that's the whole idea. Now the problem is to define composition. So let me just draw the last picture, a diagram. Okay, so I would like to draw from right to left because then the composition corresponds to the algebraic composition. So M1. We have a relation here. A closed Lagrangian submanifold with a lambda structure, so S vanishing. And then we have another one. And now we have to compose those somehow in drawings, like curly lines from here to here. And I would like to get a line from here to there somehow. So a subbundle of sub manifold of this M3 M1 project. So how do you do that? For sets, manifolds, create manifolds of sets, it's very simple. Just take those will be just pairs of elements from here and here. Then we can take the sort of a concatenation where we take quadruples of elements, such that the first one is from here, the second one is from here, the third one is from here, but they coincide, and the fourth one is from here. So it just concatenate them in a way that fits together, and we can do that for Courant algebroids, fiber-wise, and here we could repeat it in a splitting, degree-wise in a splitting. But we can also, again, it's better to see in this picture, because what we're talking about is basically, so those are the same. And we want to get some kind of a, minimal kind of structure that has the information contained in R prime and R, such that they coincide here. So it's really just a kind of a fiber product. So yeah, let's do this. Just which we could define as a limit of this pattern. So kind of a pullback. Now this might not exist, and we need some kind of transversality conditions. And so this is the first complicated part. This may not exist, and we need to check certain conditions. And the precise conditions were formulated by NQP for Courant algebroids. So we can change them, just can go to splitting and change them degree-wise in the splitting. Then we know that this makes sense, in the splitting, and then we can recover the manifold. Okay, so that's the first part, but that's still not a submanifold of this thing. We want to somehow get rid of the gluing data, the M2 data, because we get something instead we pairs of elements from M1 and M3. So we forget about the gluing data. So, but of course, to forget about them in the minimal way, we don't want to forget anything else. So we can just take, basically we just take the canonical map to the product, just the product as the universal property of the product. So it's something like this. B projection to R prime.
It's not very visible.
Yeah, it's not searchable. Yeah. And with this denoting the image of this map. So this is really, this is a we want this to be a closed, Lagrangian manifold element structure here, and we define it simply as just the image of this this map given by the universal property of the product. And again, there are certain transversality conditions on this map. In particular, it has to be a subjective submersion, and again, it can be checked as splitting, and we can use the theorem of for Courant algebroids ISP. And this shows that this thing is really well defined given the transversality conditions. And and this is how we define composition R those two constructions. So I run out of time, so that's all. I would just note that this construction and the precise transversality conditions coincide with the conditions on composition of morphisms in the so-called quantum of symplectic category defined by Scherer. where we take delta functions supported on Lagrangian submanifolds as morphisms, and we define the composition as by integration, over so this thing. Now this thing makes sense precisely, when given those resulting conditions. So that's the application, and last thing, there's two theorems which talk about the objects and basically morphisms, the two relations can be extended into an equivalence category. This thing with those relations is not a category because not all relations can be composed. But if we take formal sequences of those relations with some equivalence class, then it is a category. Those two theorems define an equivalence of categories. This bijection is precisely the bijection on morphisms, of the essentially subjective function that realizes the equivalence, and the way we extended, the way I extended it to this equivalence of actual categories is precisely the construction of the syntactic category and those delta functions, delta semi-identities supported by submanifolds. So that's it.
Yeah. Thanks to the speaker for a nice talk. And, is there any question, remark? Or I noticed that there are two remarks in the chat. Mm-hmm. One remark from Jan, rather comment that the lambda structures are also known as DG Lagrangian submanifolds. Yeah. But if anyone has something to add to this terminological comment, this is maybe the best time to.
Yeah, the DG Lagrangian sounds maybe more transparent than this, but this is what appeared in the homotopization package, Schirmer's paper. So it sticks to that. Also, given that, I'm not talking I'm saying it from in the NQP language. It's kind of the same as I could reframe it in the DG language, but this is like more tailored onto this kind of terminology. So just follow. Mm-hmm. Sure.
Yeah, sure. And there is another remark by Fritzo, which has been posted on the way during your talk. So Fritzo, are you with us? Can you?
Yes. I was just saying that that statement that you can relate an NQ manifold to a subset of bundles, that although it's related to Bachelor's theorem, so Bachelor's theorem seems to be a little bit. I would not say it's a generalization of that, because in Bachelor's theorem has this difficulty that when you are working with general supermanifolds, then you can have two functions which multiply, and you can have two odd functions which multiply and you give you an even function. But this NQ setup is the advantage of working with that is that you can never have that. So because you only have grading in one direction, so as soon as you have functions of like some non-zero degree, then you multiply them, you get something higher. So this kind of, I think, simplifies the proof. So Bachelor is kind of an analogous statement, but it's not like one of them is the generalization of the other.
Yeah.
Thank you for a very nice talk.
Maybe I guess the fact that multiplication can't like always goes degree higher is precisely what makes non-negatively graded manifolds much easier than Z-graded manifolds, because there are of course those former problems with if we say it's a local ring space, then that's not here. It's kind of trivial, but in the Z-graded setting, it's not generally true. The rings are not local. There can be some kind of the problem is precisely that non-trivial stuff can happen when we multiply degrees with both positive and negative coordinates with both positive and negative degrees, and that's the whole source of this complication. Here this doesn't happen, and then the proof proves that the rings are really local, so that it makes sense to define maybe tangent space and so on are pretty kind of trivial. So here I can just I'm talking about the talk was here summer spring. It was called Some Issues of Graded Manifolds. The problem is explained, and it's clear that graded manifolds.
Maybe I would have one question or remark. During your explanatory speech about structure sheaves, which somehow essential in definition of graded manifold, you claimed something like 0 degree functions might be, for instance, forms with Lie algebra valued in Lie algebra.
Yeah.
But I have a little problem with it, because as far as I know, those things are defined only afterwards. After you define something like function, you can say what's the differential form and stuff like that. So it is what you meant before, or is there any other approach saying these plain 0 degree functions are already some differential forms?
Yeah, it was just in the sense that of the crude analogy between so we have those coordinates x, b, sine, theta on our NQP manifold of degree 2. So this is degree 0, degree 2, degree 1, degree 1. Those two are conjugate, and those two are conjugate. And this is all we need to define the BRST charge. And basically, yeah, we can think of this. So write down, this. And now if we so that was saying that those xi coordinates correspond to the gauge fields like the connection manifolds. It was just this kind of an analogy. A the anti-field, it goes and anti-goes with some indices. And the action will have the same kind of a form. So this connection one form would play the algebraic role of those functions. So I'm not defining those as those. I'm just saying that if you look at the BRST charge, there are all Yes, so just this yeah,
You can actually take some tangent spaces of those grade manifolds and say my new fields, my new functions on this tangent space is in one-to-one correspondence with differential forms. This is quite standard trick how to define this part of differential geometry in graded language. But yeah, would simply turn out to be the same as take it degree-wise or component-wise, just as to say our forms are differentials on the ordinary functions on 0 degree part of your grade manifold.
Yes, so yes, so this is basic construction where you define a graded manifold of degree 1 as it's just shift on like or the basic trick and but then that's not what I meant here, because this way you define the odd coordinates or degree 1 coordinates, and this is really just an analogy. This should be made precise within the AKSA sigma model formalism, but here it's just like here I would replace those psi's with the ghosts, P with A star, and it's with the ghost again, and and all the derivatives with functional derivatives, and so that's the analogy.
Okay, fine, thank you. Is there any other question in your hands?
Maybe I have one question. Maybe I should also know the answer, but I haven't got that right now. Do we have the results about NQP manifolds of degree bigger than 2?
Yeah. So there are some. So first, why do we do? Why we care about it? Not why not talk about all the degrees or degree 1 or something? Because degree. If I have more time, I'll definitely say a bit more about degree 1 and NQP manifolds, because they're they're precisely the algebroids. Like NQP manifolds are precisely the algebroids, and if you add the P structure, you can think of them as Poisson manifolds. So NQP manifolds in degree 0 are just symplectic manifolds. In degree 1, in degree 1 it's Poisson manifolds, and NQ are the algebroids. So that's a first kind of a generalization that we go from the symplectic world to the Poisson world, which is a bit more complicated. And but the next step is really interesting in the sense that we're not talking about we can model it as a single vector bundle. So it's not like this thing is just a vector bundle. Like every graded manifold of degree 1 can be thought as sort of like this, and we wouldn't have functions of this form, functions where we wouldn't have affine coordinate transformations. So because like this P coordinate, so degree 2, so like P prime would be something with P plus something, and 2 coordinates of degree 1. So is the first degree where the affine transformations come in, and where the different start to communicate non-trivially. And this communication is precisely the like the way the way the pairing a Courant algebroid communicates with the Lie bracket. So how it deforms the Lie bracket into the Courant bracket is that's it. That's the that corresponds to the language of NQP algebras. You know, taking saying that it's a Lie bracket up to some higher stuff. So it's really the first part where we are talking about like higher geometry in a sense. And yeah, and okay, so that was the first part. Why degree 2? The second part about higher degrees. Yeah, there's something. Okay, you can 2000 something. Okay, that's 0 for sure. And maybe it's actually not even 20. I'm not really sure. I will. Yeah, but if you can add some right keywords like Courant or symplectic differential, you should find a paper where he talks about this, about the construction of a Courant algebra from an NQP manifold, and he goes further and says a bit more about the higher part, higher degree 3. It's pretty. It's quite detailed in a lot of calculations in coordinates as well. But yeah, it's quite useful when you want to see the precise calculations. So there is something and the thing is that you just get more of those terms. There is now there's something with more indices. And it goes on, and yeah, so there are some results of this. And here can be seen as those things can be seen as can be thought of as the structure constants of like higher brackets, higher altitude.
Thanks very much for nice answers, and I'm afraid we need to evacuate the room. So thanks again.
Yeah, thank you.